Hey everyone, welcome back to Explore Electronics. Here we will see the module 1 of Introduction to Electronics and Communication Engineering. It has power supplies and amplifiers as two chapters. Let's start with power supplies. In the second half of the video, you see amplifiers. Block diagram of a DC power supply is as shown in the figure. In this block diagram, you can observe a high voltage AC is given as input here, and finally we are going to get with a regulated DC output. Once we given the AC voltage to the step down transformer, we are going to get a low voltage AC as output of the step down transformer. And that is an input for the rectifier. Rectifier is going to convert an AC signal into DC. But the output of the rectifier will be unsmoothed DC signal. To smooth that signal, we need to have a smoothing filter and a reservoir circuit. And then the output of that will be smoothed DC, and that will be given to the regulator to get the regulated DC output. Now let us see the block one by one. First we will be having a step down transformer. The step down transformer is that it will be having two coils wounded to a iron core. One will be called as a primary coil, to which we are going to provide the high voltage. And the secondary coil will be having less number of turns compared to primary coil, and the output will be taken at the secondary coil. And here you can observe the high voltage AC is converted into a low voltage AC here. The step down transformer is going to reduce the amount of voltage. And next we will be having a rectifier. Rectifier is a device that is going to convert AC into pulsating DC. So in the figure you can observe here in the waveform, the AC voltage which is coming out of the transformer is like this, and it is removed the negative half cycles, only the positive half cycle of output we are going to get as output of the rectifier. But here you can observe it will be consisting of an AC component, means that is what the unsmoothed DC we can say. So we are going to give this signal to an reservoir or smoothing filter circuit. This reservoir, what it is going to do? Reservoir will be having a capacitor circuit, and smoothing filter again will be having within the device. It is going to smooth the signal by removing the ripples. You can observe here, this is what the filtered output we are going to get as output of this particular block. And that will be called as a smoothed DC signal. And that will be given to the voltage regulator. Voltage regulator will be having an active component like transistor and a diode arrangement. Zener diode will be generally used, and we are going to get a DC output like this, steady output like this, that will be called as a regulated DC output. Here the regulated DC output, in the sense, even if there is a small variation in the input of the voltage regulator, it will regulate the DC output, and we are going to expect a constant output from the voltage regulator. This is what the block diagram of the DC power supply. Here you can observe the components like step down transformer, it is having a coil, and in place of rectifier you can observe here this is a bridge rectifier arrangement, and then reservoir and smoothing filter we can have a capacitor like this, and voltage regulator we will be having a Zener diode as well as the transistor arrangement. These are all the principal components present in these particular blocks we can say. So the real-time example of a DC power supply device, it will be like this. You can observe here there is a transformer, a step-down transformer. The input of the transformer will be an AC input, and it is going to give the output from the secondary. We will be having a bridge rectifier circuit here to convert that AC into pulsating DC. And we need to smooth that signal, that's why we will be having a reservoir capacitor here. You can observe here this is a capacitor, and we are going to get an output from the regulator, that is the DC output, right? And to for the safety purpose we will be having fuse at the primary of the transformer as well as the secondary of the transformer. And here we need to understand rectifier is the one of the main component in DC power supply. While converting an high AC into DC, we need to have a rectifier. So the definition says rectifier is a circuit which converts AC signal into pulsating DC. So here we need to understand AC signal to pulsating DC means the DC signal coming out of the rectifier will be having AC component that will be called as pulsating. And here generally we are going to use semiconductor diodes to convert the alternating current, or we say alternating signal, to direct current or the direct signal. And you can observe here the semiconductor diode, how actually it will be. It will be there in rectifiers. This is what the symbol of the diode. It is a triangular symbol with a dashed line like this. This end will be called as anode and this end will be called as cathode. It will be having a PN junction. P region as well as N regions are connected together and it is forming a junction in between. And this is what the component of the diode which is available in the market. It looks like this. And this end is anode, and here you can observe a silver line indication of cathode, that is negative. And how this diode is going to function? If we connect the diode to a positive power supply and other end of the diode is connected to the negative power supply, then we say it is forward biased and diode is going to conduct. The current flow in the diode will be in this direction, and diode will allow the current to flow in only one direction. And when it is reverse biased, means negative power supply is connected to the diode anode and the positive terminal will be connected to the cathode, diode will be reverse biased and there is no amount of current flow in reverse direction. That's why we say when the diode is in forward biased, it will be conducted. When it is in reverse bias, it is not going to conduct. And how this diode is going to work? When we connect an AC signal like this, see now the positive half cycle of the input is giving to the diode and diode will be forward biased and conducts. When it is negative half cycle, diode becomes reverse biased and it will not gives any output. 0 will be the output when the negative half cycle of the input coming to the diode. And as the positive half cycle of the input comes, diode will conduct. That's why we are getting the same kind of output here as it is in the input side. Next we have rectifier circuits. By using this diode functionality, we can have different kind of rectifiers to convert an AC signal into DC signal. The first one is half wave rectifier. What is half wave rectifier? Half wave rectifier is a device. It is going to convert an AC into pulsating DC, but the output of the half wave rectifier will be half cycles if we compare to the signal at the input. So let us understand what is half wave rectifier. So in this circuit, you are seeing a simple half wave rectifier circuit, which the input will be 240 volts AC signal. Here you can observe this is an AC signal we are connecting as input to the transformer, primary coil. And at the secondary coil, we are going to get equivalent 12 volts, means this is a step down transformer. It is reducing the voltage from 240 to 12 volts. And we are connecting that to the diode D1. And this, as we know, diode D1 conducts when it is forward biased and diode D1 is off, or it will be not conducting when it is reverse biased. So we will be having a load here, that is RL. We need to observe the voltage across RL so that we can observe the voltage generating from the rectifier. So to understand this, we need to look at the input we are giving and what actually the output it is going to give. This is the AC signal we are giving, the large AC signal, and it is converting into pulsating DC like this. At the positive half cycle of the input, we are going to get the output as it is with the reduced voltage, and in the negative half cycle of the input, diode will not conduct and output will be 0. And here is the explanation for that. When the positive half cycle of the input is connected, given diode D1 conducts, that's why the switch is closed here. This will make the path to current flow. The current flow will be in this direction, right? So across RL we are going to get the output like this. When it is reverse biased, means the negative half cycle of the input is given. What happens? Diode becomes reverse biased. Diode reverse biased means diode will be off. So the switch is open. there is no connection between this end to this end. So there is no current flow. When there is no current flow, there is no output across RL. That's why here in the previous slide we seen the output will be only half cycle. The negative half cycle of the input comes, there is no output here. Here is the waveform that gives the meaning to this particular operation of half-wave rectifier. Here the blue wave indicating an input signal and the red line indicating an output signal. You can clearly observe in the positive half cycle we are going to get the output, and in the negative half cycle there is no output generated. This is the output of the half-wave rectifier. We can plot like this. And in the DC power supply we have seen, after the rectifier we will be having a reservoir and the smoothing circuit. This is what the reservoir and smoothing reservoir circuit, half-wave rectifier connected with a capacitor filter. This is the extra capacitor we have connected here. Once we connect this capacitor, what happens? It is going to smooth, or it is going to reduce the pulses in the output of the half-wave rectifier. Means we say ripples present in the output that can be eliminated. You can observe here the T1 secondary voltage is this, peak to peak it is plus 17 and minus 17, and voltage across RL without C1. Without C1 in the sense without connecting this capacitor, this will be the output. And by connecting C1, what happens? This capacitor is going to be charged initially. Up to here it is going to be charged, and when the voltage reduces, what happens? Capacitor will hold the charge until the next positive value comes, and it start discharging as time goes. By that time it is getting the next positive value. So again it is going to be charged to the next peak value. The process continues. So what we are going to get advantage here, the ripples present over here is going to be eliminated and the curve becomes smoother. This is how we can reduce the amount of AC component present in the half-wave rectifier output by connecting a capacitor like this. This capacitor will be charged, and then it is holding its state, and as time goes it is discharging its value. By that time it is getting the next peak value, and again it is going to be charged. So this is how we can smoothen the output of the half-wave rectifier by connecting a capacitor. And here is the another circuit by connecting RC smoothing filter. Here is the filter arrangement. You can observe this R1 and C1 is the filter circuit which we have connected extra with this capacitor, reservoir capacitor. Here what is the advantage? Here the advantage is that it is going to reduce the ripples again. This makes the circuit output smoother. Here R1 C1 is act as a filter which will remove the ripples, and the value of C1 we need to choose carefully so that the component exhibits a negligible reactance at the ripple frequency of 50 Hz for a half-wave rectifier and 100 Hz for a full-wave rectifiers, which we have full-wave rectifier we are going to discuss later. And the effect of this R1 and C1, in the sense this arrangement, filter arrangement, it will be act as a voltage divider. Okay, and the amount of ripple reduced by an factor across this capacitor, if we observe what actually the amount of ripple voltage reduced, can be calculated by this expression. XC is the reactance of the capacitor divided by root of R square plus XC square. So here XC is the reactance will be 1 divided by 2 pi FC. F is the frequency of the signal and C is the value of the capacitance. And next we have full wave rectifier. As we know, the half wave rectifier is giving the output pulsating DC, but it will conduct only at the positive half cycle of the input. That's why we are going to get only half cycle output, and at the negative half cycle of the input we are not going to get the output in half wave rectifier. That will be eliminated by the full wave rectifier circuit. In full wave rectifier we are going to get the full positive cycle output even in the negative cycle of the input. That we need to understand here. So basically we will be having two types of full wave rectifiers. One is biphase type, it will be called as center tapped full wave rectifier, and also we will be having bridge type rectifier. So we'll see one by one now. First we will be having a center tapped full wave rectifier. So the center tapped full wave rectifier, in the arrangement itself you can observe it will be having a transformer. The primary coil will be connected with an AC signal, and at the secondary coil we are tapping the secondary coil and taking an signal here, and the secondary coil will be connected to another end of the load, and another end of the coil will be connected to the load RL. You can observe here the output of this particular rectifier is taken across RL here, across these two ends. It is from one end of the coil and with the center tapped arrangement. And two diodes are used here, D1 as well as D2, and this makes the center tapped full wave rectifier arrangement. Here also we are going to give a 240 volts of AC signal, and the available voltage at the two ends from AB and also to B to C is 12 volts RMS value. 12 volts RMS value, which is equivalent to 17 volts AC signal. So let us see how actually this center tapped full wave rectifier is going to work. Here we will be having two diodes, let us call it as D1 and D2. When the positive half cycle of the input is given to the primary coil of the transformer, it is a positive half cycle of the input. It is making the diode D1 forward biased and D2 reverse biased. Because of the center tap here, the diode D1 will treat that as a positive signal and D2 will be treating that as a negative signal because of the positive and negative arrangement you can observe here. So D1 becomes forward biased and D1 conducts. D1 is conducting and the current will be flowing in this direction through RL and it will coming back to the negative terminal here. And because of the forward biasing, diode conducts the current flowing through the RL in this direction. The voltage across RL, if we measure like this, it is same as the input signal what we have given. Similarly, when the negative half cycle of the input is given, negative signal will be having the value negative with respect to the origin is concerned. Here it will be treated as the forward biased voltage to the diode D2. Diode D2 will be treating that as a positive voltage. Diode D2 conducts and D1 will be off. D1 will be off because it is reverse biased. So D2 conducts. Because of D2, the current will flow in this direction and it will make a path like this and it will flow through RL and it is come back to the negative terminal of the center tap. So again you can observe here the current flowing through RL will be in the same direction. So if you measure the voltage across these two ends, current flow will be in this direction. Again the voltage will be in the positive half cycle. You can observe here the voltage here it is generated is also same as the negative half cycle input. The voltage will be in the positive value. So the full wave rectifier is going to generate the signal as DC with this kind of output. Here even in the negative half cycle we are going to get the positive output. Now let us understand how actually this center tapped full wave rectifier will work. For a positive half cycle, the diode D1 conducts and D2 is off. So the positive half cycle of the input comes, D1 will allow the current to flow through, that current will flow through RL and output will be generated like this. Okay. Similarly, let us understand the negative half cycle of the input. When the negative half cycle of the input is given, it will be treated as a positive voltage for D2 and D1 becomes reverse biased. That's why D1 will not conduct, only D2 conducts, and again the current flow through RL is in the same direction. Here the circuit is modified to make it understand better. So you can observe the current flowing through RL in the same direction as the current flow through the RL in positive half cycle of the input given. That's why we are going to get the same peak value like this even in the negative half cycle of the input. This is what the advantage in the full wave rectifier. We are going to get one more signal here in the negative half cycle also, so that we are going to get a better DC output. This is what the output of a full wave rectifier for an AC signal. And again we can connect a reservoir circuit and smoothing circuit for the full wave rectifier as we connected in half wave. This C1 will be acting as a reservoir capacitor. This is what the secondary coil voltage 17 volts, and at the output of this RL without C1 we are going to get the signal like this. Okay, and it will be consisting of more AC component compared to the half wave rectifier output. So we need to reduce this AC component and we need to get the DC voltage something like this, a steady output. So to reduce this AC component, what we are going to do, we are going to connect this extra capacitor C1. What this capacitor is going to do, when the current is started to flow in this direction, even in the positive half cycle of the input and the negative cycle of the input, the capacitor will charge to its peak value. So capacitor will be charged to this value and it will be holding its value. And when the next positive edge comes, again it will be charging to that particular value, and meanwhile it is started discharging, but by that time again the next value of the peak signal comes to the capacitor, again it is going to be charged. Compared to the half wave rectifier, here the voltage getting to the capacitor C1 is more sooner than the half wave rectifier. That's why here in the full wave rectifier we will be having less more steady output compared to the half wave rectifier. This is what we are calling it as a ripple. The amount of ripple voltage is this much. Okay, so to reduce this, again we can reduce the amount of ripple voltage here. That's why we can connect one more capacitor and resistor arrangement as a filter circuit. That as we discussed in the half wave rectifier, the same kind of arrangement we can make here also. This is an full wave rectifier circuit. So next we will be having a bridge rectifier circuit. Bridge rectifier is again a full wave rectifier. It is working same as a full wave rectifier, but we can have a bridge kind of arrangement of diodes to get the pulsating DC output. It will be called as a bridge rectifier circuit. It will be consisting of 4 diodes which is connected in a bridge fashion. So the diode arrangement will be like this. If we connect this diode like this, and it will be like opposite pair of diodes conduct when the alternating half cycles are coming into an input. Means this diode and this diode will conduct once, and in the negative half cycle or the second half cycle this diode and this diode will be conducting. The arrangement will be like that. Now let us see how actually this bridge circuit will work. So again there will be a transformer at the input. It will be having a primary coil connected to a 240 volt AC, and there is a secondary coil. Secondary coil will be giving the step down voltage something like 12 volts RMS, and it is connected to the diode arrangement. Here 4 diodes are connected in this fashion. You need to remember how the diodes are connected, and they are named as D1, D2, D3, D4 as opposite diodes conducting at that particular time. So at the two ends of this bridge arrangement we will be having a load RL, and current will always flow in this direction through the load. So we are going to measure the voltage across this RL. Okay. In the positive half cycle, what happens? When the positive half cycle of the input is given to the rectifier, D1 and D2 conducts. This D1 becomes forward biased and D2 becomes forward biased. The current will flow in this direction. Okay. So you can observe here, this is what the path it is going to take to reach the P point when it is the positive half cycle of the input is given. And what about D3 and D4? They are reverse biased and there is no conduction in D4 and D3. And the negative half cycle of the input, is given. What happens? D4 and D3 becomes forward biased. So the current direction will be like this. The current will flow through D3 and again through RL, it will through D4, it will reaches the other point. This is how the bridge rectifier is going to work, and the direction of current will be same in this direction. Okay, so let us understand the working. Here you can observe when the positive half cycle of the input is given, D1, D2 are connected, means D1 and D2 are forward biased and making the circuit closed switch, acting as a closed switch, and the current direction will be shown here through D1 and then through RL, and then it will flow through D2 and it is completing the circuit, and current flowing through RL is in this direction. The output can be measured across RL and output will be again in this manner. When the negative half cycle of the input is applied, the current flow will be in other direction. D1 and D2 becomes reverse biased and D3 and D4 becomes forward biased. So the current flow will be in this direction through this path through D3. Since D3 is forward biased, it will make the path to current flow through RL. Again it will go through D4 and it will reach us the other point. Here also the current flow direction will be in the same manner, in the same direction. That's why again we are going to get the same kind of output as we get in the positive half cycle. This is the bridge circuit. Here you can observe the current flow direction when the positive half cycle of the input is given. Here the diode, the name of the diodes like D1, D2, D3, D4 is interchanged, means D3 in place of D3 they have written D4, but the direction of current is same. So this is what the positive half cycle of the input is given and how actually the current flow will be. And if you look at the negative half cycle of the input, is given. So this will be the path. It makes D4 forward biased, the positive voltage makes the D4 forward biased, and also through this path D3 becomes forward biased. That's why the current is flowing through D4, through RL, through D3 and to the negative terminal. So here we are going to get the output same as the positive half cycle, right? So full wave rectifier output, as we seen in the previous slide, that is a center tapped full wave rectifier. Similarly here we are going to get the output. This is how bridge rectifier is going to work. Here you can observe the output, it is same as the full wave center tapped rectifier. Both center tap as well as the bridge rectifier output will be of same kind. So to connect a capacitor filter or the reservoir circuit to a bridge circuit, it look like this. Again across the load resistor we are going to connect a capacitor. This capacitor arrangement will reduce the amount of ripples present in this particular output. Without capacitor we will be having more AC component or ripples will be present. After connecting a capacitor, it will remove the ripples present in the output by making the capacitor charged to the maximum value, and it will retain its value, and it is again charging when the next peak comes into the capacitor. That is how we can reduce the amount of ripple getting at the output of the rectifier. What is voltage regulator? Voltage regulator is a device, it regulates the voltage level. Means it steps down the input voltage to the desired level and it keeps that voltage as constant during the power supply. Even if power supply varies, the output of the voltage regulator will be a constant DC voltage. So you can observe this is an example for that voltage regulator circuitry. Even if there is a variation in the input voltage coming to the regulator, this voltage regulator will regulate that to 5 volts constant voltage that can be applied to a mobile phone like a device. We call it as load for a charger. Even if load varies, means the mobile phone changes, it requires 5 volts supply. That 5 volts will be a constant voltage we can get from the voltage regulator. So there are different voltage regulators with respect to the voltage regulation is considered. 5 volt, 9 volt and 12 volt regulators are also available. This is the simple Zener diode based voltage regulator we are going to discuss here. The Zener diode is heart of the circuit here. This Zener diode will be connected in the reverse biased fashion, and RS and RL are the resistances. RS is connected in series, so it is called as series resistance to limit the current to the Zener diode, and this is the load resistance. So let us understand the working of the Zener diode first. The Zener diode, if it is connected in forward biased manner, if it is connected to a positive power supply to anode and negative power supply to cathode, it will be act as a normal PN junction diode. You can observe the forward biased characteristics here. After the cut-in voltage, it varies from 0.3 to 0.7 depending on the silicon or germanium diode. It will start conducting. In the forward biased condition, it will be act as a normal diode. When it is reverse biased, we need to understand carefully. When the Zener diode is connected in reverse biased fashion, you can observe there is a small amount of current, negligible amount of current flow until the point Vz. Once it reaches the Zener voltage, we call it as the Zener voltage Vz, even if current increases to the level of Iz and Iz minimum, the voltage will be constant. Means it will allow the current within the diode up to Iz maximum and at the same voltage Vz. So this functionality can be utilized as a voltage regulator circuit. So Zener diode is connected in a reverse biased fashion, is utilized here as a voltage regulator circuit. In this circuit, we have RS that is connected to the input of the Zener diode, we can say. So here we are going to get Vz. From these two terminals, if we measure, we are going to get a voltage Vz for a input Vin. So this is a voltage divider kind of circuit here, right? So here we will be having RL across this. So across these two ends, we are going to get a voltage called Vz. It can be written as Vin into RL divided by RL plus RS. So RL is a load resistance and RS is the input resistance. We need to choose this RS carefully. We need to understand what is the maximum level of RS we can give. So the maximum value of RS is RS maximum is equal to RL into Vin divided by Vz minus 1. And the power dissipation across the Zener diode will be Pz is equal to I into V, that is Iz into Vz. The minimum value of RS, what we can have when there is an off-load condition, it is RS minimum is equal to V in Vz minus Vz square divided by Pz maximum. Here Pz is the maximum power dissipation across the diode we can have. So across this RL, if we measure, Vz is the voltage we are going to get as a constant value because of the Zener diode. And then output resistance. Output resistance R out can be written as change in output voltage with respect to change in output current. Voltage divided by current is the resistance, as we know. The output side resistance can be measured as a change in voltage output with respect to change in output current. So the regulation of a power supply is given by the relationship. What is the amount of regulation occurred? So regulation is equal to change in output voltage divided by change in input voltage into 100. Ideally, any Zener diode voltage regulators will be having a regulation of 5% to 10%. As low as the regulation percentage, the regulator will be good. Then we will be having voltage multipliers. These voltage multipliers are very much important to double the voltage or to triple the voltage. So here we are going to discuss voltage doubler circuit, and next we will be discussing voltage tripler circuit also. Here in the voltage doubler circuit, we will be having a transformer where an AC signal is given here as an input. The secondary coil will produce the same kind of output here. We can use a step down transformer if it is required. So here you can observe there are two diodes and two capacitors connected, and there is a resistance RL. Here in this arrangement, C1 and C2 are going to be get charged. Across C1 and C2, if you measure the voltage will be doubled compared to the input. Now let us understand the working or the operation of voltage doubler. When the positive half cycle of the input is given, that is available over here at the secondary coil of the transformer, and D1 becomes forward biased, and we can say that is a closed circuit, that makes the closed path. And what about D2? D2 becomes reverse biased, and D2 will be a open circuit. In this condition, the current flow will be in this direction. The current flow through C1, it makes the C1 to charge, and this is the way the current is going to flow. And this C1 is going to be charged to the peak value of Vin. If the peak value of Vin is taken as Vm, the capacitor will be charged to that level. So now C1 will be having a voltage of Vp, that is the peak voltage in this positive half cycle. What happens in the negative half cycle of the input is given? The same negative half cycle of the output we are going to get on the secondary coil, that will be given to the circuit. In that situation, D1 becomes reverse biased, and we can treat it as an open circuit. At the time, D2 becomes forward biased, and that will make the circuit closed. In this scenario, the current will flow in this direction to C2, and C2 will be charged to the peak value of the voltage. So C2 gets charged in this direction. The voltage available across C2 now it is Vp. So C1 is also charged to Vp, C2 is also charged to Vp. So if we measure the voltage across this RL, it will be 2 times Vm, or if we take this as P, it is 2 times Vp. That voltage is the available voltage here. This is the peak voltage. We can treat it as Vm. So 2Vm is the output across RL, means the voltage is doubled. So the next topic is switch mode power supplies, that is SMPS. So here SMPS is the device which will provide all the required input current and voltages in CPUs. If you see CPU, there will be a device called SMPS. That is what switch mode power supplies is. So in the power supplies, we can divide into two types. One is linear, another one is non-linear type. Linear power supplies, in the sense, that is what the conventional analog control techniques it uses. Means the regulating devices operates through continuous range of current and voltages, and according to the input and load conditions at the time. That is linear power supply. Non-linear power supply, in the sense, it uses some digital techniques there, and where the regulating device is switched on rapidly on and off in order to control the current and voltage what it gives to the load. So that is what non-linear power supply is. So here SMPS is a type of non-linear power supply. The non-linear power supplies are commonly referred to as switched mode power supplies. We call it as SMPS. These devices can step up and step down the voltage. If it take the input coming to the SMPS can be increased, used as step up, or we can use it as step down to reduce the voltage. There are some advantages of SMPS here. They have an ability to give wide range of input voltage range, and very high efficiency they will provide, and they are compact in size, and they are also lightweight devices. And the disadvantages are like it has some complex circuitry, and noise generated by the device will be high. That is what the advantages of SMPS and disadvantages. Coming to the circuit, you can see these two circuits here, where the first thing is, here we have a switch called S1. The first circuit says what happens when the switch is closed and what happens when the switch is open. I said here these non-linear supplies will be work on the regulation of the device through switch on and switch off the device, right? To do that, we have S1 over here. The first circuit is switch closed. When the switch is closed, here we have a diode. This diode will be reverse biased and it is off. It will not conduct. There is an inductor here, current flow through the inductor, and there is a capacitor here. This capacitor will be charged and this will give an output I out as a current here to the load RL. Means I out will be the constant current which RL gets. Then when the switch is open, what happens? When the switch is closed, this IL will be the current flowing through the inductor. There will be an magnetic flux induced. When the switch is open, there is no magnetic flux induced here, but there is a voltage developed in the reverse fashion across the inductor. This is positive, this is negative. Because of that, the current flowing through the load will be in the same direction. You can see I out will be in the same direction. And since it is negative terminal and current flowing in this direction, this becomes a positive terminal to the diode. Diode will be on. Because of diode on here, there is a complete path to the current flowing to the inductor's negative terminal now. This is the way this device SMPS behaves when switch is on and switch is off. There is a waveform shown here. The inductor voltage, what it is there when switch S1 is closed and S1 is open, and also the inductor current. Okay, this is just to understand the inductor voltage will be more positive when the switch is closed and it will be negative when the switch is open, and diode will be on, diode will be off in those two cases as we understood. And the average current flowing through the inductor is shown over here. That will be equal to the load current always, that is I out. Okay, there are some ripples here present. These ripples can be eliminated or reduced by using a large capacitor in the circuit. Okay, then we need to understand this switch what we have here in this circuit can be automated to open and close by using an transistor. We can use a BJT or we can use a MOSFET over here. So this S1 will be replaced by a BJT now. This BJT having base of the device here. This base is provided with an alternating signal like this square wave. This circuit will be open and close, right? To do that, we require a BJT or MOSFET here. Okay, and with this, we will be having a power supply control device. Control device in the sense there is a available device here. You can see LM78S40. This is what the circuit is. This is LM78S40 is a switch mode power supply controller. This will be used as a monolithic switching regulator system, which can step up the regulated voltage, which can step down the regulated voltage, which can invert the regulated voltage. Okay, so here the core of the system is that it will be having an arrangement of Q1 and Q2 transistors here, and there will be a diode D1. These three are controlled by the internal oscillator OSC. This oscillator provides continuous signal, which this SR flip-flop what we have, this makes that to be switch on, switch off this Q1, Q2. So these devices, oscillator and IC1, IC2 are two comparators. These are op-amp devices. All these constituting a power supply controller. Okay, and this device give the current limiting circuitry to maintain the desired output regulation. This device will be just a power supply controller device. This is about SMPS. First, what is an amplifier? Amplifier is an electronic device that can increase the power of the signal, or we can say amplifier circuit is going to increase the strength of the signal. So if you apply a small voltage signal like this to an amplifier, the output will be a large signal you can observe here. So amplifier is going to increase the voltage or the power of the signal. So we say the output of the amplifier is V out will be equal to AV times V in. What is AV here? AV is the gain of the amplifier. The amount of amplification it is produced is called as gain. So the expression for gain can be written as V out divided by V input. This is the practical example of an amplifier device we are going to use. A microphone, it takes an audio input. That audio will be having a less voltage. So that will be connected to an amplifier. Amplifier will increase the strength of the signal and it will be given to the speaker, where the speaker output can reach to the maximum distance. So next we have type of amplifiers. We need to understand the different types of amplifier circuits available. One is AC coupled amplifiers. Here we need to understand the coupling. What is coupled amplifier means? Coupled amplifier in the sense we are going to use 2 or 3 or 4 stages of amplifiers connected together one after the other. So in this particular type, AC coupled means only AC component of the signal is going to be transferred from one stage to next stage. Such amplifiers are called as AC coupled amplifiers. Next we have DC coupled amplifiers. Here also the number of stage of amplifiers circuit is there, where both DC and AC component of the signal is going to be transferred from stage to next stage. Then we have large signal amplifiers. These kind of amplifiers is capable of amplifying the large voltage signal or the high current level inputs. If we are going to provide an input typically from 1 volt to 100 volts or more than 100 volts, the amplifier is able to amplify that signal to the next level. That is called large signal amplifiers. And we have small signal amplifiers also. Small signal amplifiers in the sense very low voltage signals or the very low power signals are going to be given as input for the small signal amplifiers. It will amplify that to the next voltages. Also we have audio frequency amplifiers, where the inputs are only the signals which are come under an audio frequency. The audio frequency in the sense it is in between 20 Hz to 20 kHz. The audio signals will be having the frequency in between these two frequencies. Those kind of amplifiers which are going to amplify only audio signals are called audio frequency amplifiers. Wide band amplifiers. Wide band in the sense, as the name itself says, the frequencies which the amplifier is going to amplify is having wide range. Means from 10 Hz to several megahertz of frequencies, the amplifier is capable of amplifying the signal. That is wide band amplifiers. And then radio frequency amplifiers. You might have known the radio frequency will be from 100 kHz to over 1 gigahertz. These range of signals will be called as radio signals. So this radio frequency amplifier is going to amplify that range of signals. Then low frequency amplifiers. Low frequency amplifiers in the sense low noise amplifiers we can call, so that they contribute negligible noise to the signal being amplified. So usually it is having the voltage levels less than 10 millivolts, very less voltage signals we can say. These are the different types of amplifiers available. So what is then amplifier gain? What it means? Gain is an important parameter which can define an amplifier, the amount of amplification it is going to provide. What is the gain we are going to get from the amplifier? That is how we can understand this. So you can observe in the figure here, the diagram, the input we are giving V in is very small, V out is very large. And with respect to the input side is concerned, we have I in, you can observe here, this is input side current, and similarly I out is output side current. So voltage gain in terms of AV, if we write, that is V out divided by V in. V out, output voltage, to the input voltage. Similarly with respect to current, if we take, that is I out divided by I in. The output current what we get from the amplifier divided by the input current is called current gain. Similarly we will be having power gain. Power gain is power P is equal to I into V. So we can use that formula here to write the power output as I out into V out divided by P in as I in into V in. So we can write this expression as I out divided by I in separately into V out divided by V in. So we know that I out divided by I in is AI, V out divided by V in is AV. So the power gain AP can be written as AV into AI. Then we have another parameter we need to look at, that is input resistance and output resistance. Input resistance will be an ratio of voltage at the input to the current at the input. V divided by I is the expression for R. We know the same formula here we can use to get the input resistance. Rin is equal to Vin divided by In. Similarly, output resistance. Output resistance is the ratio of open circuit output voltage to the short circuit output current. Here you can observe in the diagram, Rin and Rout are going to be shown with some internal circuitry of the amplifier. So here with respect to the resistance are concerned, we need to note these points. We are not supposed to get confused with the RL connected in the circuitry. This RL is a load resistance, or the resistance of the load what we are going to connect the output of the amplifier. Output resistance is not same as RL. Output resistance is internal to the amplifier and RL is external to the amplifier. And in some cases, when the capacitance comes into picture, the reactance of the input may become large. Means a stray capacitance appears in parallel with the resistance. In such cases, the resistance and the capacitance reactance will be totally called as input impedance, that is represented as Zi. Remember, for any amplifier, input impedance should be high, or the input resistance should be high, and output resistance should be low. Similarly, we call that as output impedance. Output impedance should be less. And then frequency response. The frequency response is a curve here. You can observe it is plotted gain versus frequency. The different kind of amplifiers we have seen, that is audio amplifier, wideband amplifier, radio amplifier, DC coupled amplifier, AC coupled amplifier, like that. So for those amplifiers, if it is an audio amplifier, audio frequency amplifier, the frequency response will be like this. Similarly, for the wideband amplifier, the frequency response will be wider like this. And for the radio frequency amplifier, this is the frequency response. What it is giving the information means, in x-axis we will be having a frequency and y-axis we will be having gain. Means for the radio frequency amplifier, we are going to get the gain only at these frequencies. The set of frequencies where the radio frequency amplifier is going to amplify is this. Here we are going to get the maximum gain. As the frequency becomes lower, it is going out of the radio frequency range, that amplifier is not going to amplify. By looking at the frequency response of any amplifier, we can see clearly from which frequency to which frequency the amplifier is going to amplify. And the gain in the amplifier is going to be represented with decibel, that is a logarithmic scale. And always the frequency, the lower frequency is something like this point to this point, we are going to take by reducing the level of gain. If it is the maximum gain is here, we are going to reduce that by minus 3 dB points, and we are going to take the frequency, lower frequency and the higher frequency for the bandwidth. So we will understand why that 3 dB is going to be taken in the other video. Then bandwidth. Bandwidth is the difference between the upper as well as the lower cutoff frequencies. If this is the frequency response, and in y-axis we are writing the gain with respect to power, this is the maximum power we are going to get from the amplifier. And the lower frequency the amplifier can amplify is f1, and the higher frequency or the maximum frequency it can amplify is f2. If you get the frequency response like this, by reducing the 3 dB gain over here, this will be the line we are going to get. At this point here, this is f1 and this is f2. If you take the difference between f2 and f1, the amount of frequency range we are going to get, that difference will be called as bandwidth. Bandwidth is the difference between upper frequency to the lower frequency cutoff. So with respect to the voltage gain is concerned, you can observe here AV maximum, and we are taking 3 dB low, that is 0.707 for the voltage. We need to multiply 0.707 for the maximum gain, so that we are going to get the cutoff frequency for the lower cutoff as well as for the higher cutoff frequencies. This is how we can say the bandwidth of the amplifier, by looking at the frequency response. And this figure might be giving the more information, where you can observe here this is the bandwidth, and we are not going to consider these two areas. Why we are considering this as bandwidth means by taking 3 dB lower to the maximum output. This is lower cutoff frequency and this is higher cutoff frequency, and this is the bandwidth. Then we need to understand phase shift. The amplifier output may be having some phase shift with respect to the input signal is concerned. So we are discussing phase shift here. Suppose this is the input signal of any amplifier circuit and the output signal may be this. Okay. So if we are getting the two phases of the signal like this, we need to get the difference between these two. The timing difference between these two will be represented with the phase angle, and that is the phase shift the output of the signal is taking. Let us understand this in a better way. So these are the different phase shifts signals, how actually they are going to look. If the phase shift is 90 degree, if the signal A is like this, and because of the amplifier the output may be something like this, these two signals will be having a 90 degree phase shift, where A is ahead of B. A is starting early than B with an phase shift of 90 degree, we are going to say. And in other words, we say A leading B with 90 degree phase shift. And similarly here, you can observe it is again a 90 degree phase shift where B is leading A. And if the signal is completely reverse like this, we say it is 180 degree phase shift. And if A and B are in the same phase, we call it as the two signals are in phase with 0 degree phase shift, or it will be a 360 degree phase shift. So we can understand this with this particular waveform. If it is starting from 0 degree going to 90, the signal is going to be changed like this. If the phase shift is 90 to 180, at 180 degree exactly the signal is in reverse order. Again, the next 90 degree phase shift it is taking, so the 270 degree it is looking like this, and once it completes the 360 degree phase shift, it is looking like a previous normal signal. This is how the phase shift of the amplifier can be obtained. You can observe here the first diagram indicating an amplifier output with 0 degree phase shift or 360 degree phase shift. As the input signal is, similarly the output is generating with amplified output. But the second figure you can observe there is an 180 degree phase shift occurred, where if the input signal goes high like this, the output signal will be generating the lower voltage like this. This is how the phase shift of the amplifier is going to be changed. And then the next concept with respect to the amplifier is feedback. What is feedback? Feedback is defined as the process of returning or giving the part of output from a circuit back to the input. Here in the figure you can observe there are two types of feedbacks. One is positive feedback, another one is negative feedback. In the positive feedback, the output is given back through the feedback circuit to the input. The feedback output, the blue wave, it is same as the input signal. If the feedback output is same as the input signal, so we say the feedback circuitry what we have used here, the mechanism is positive feedback. If the feedback output coming to the input is with respect to the input signal, if it's a 180 degree phase shifted, we call it as negative feedback. In the previous topic we have seen the phase shift. Here you can observe when we are giving the feedback output of the feedback circuit may be 180 degree phase shifted with respect to input. So here this is called as negative feedback and this is called as positive feedback. So let us understand the feedback in detail. So in amplifier circuits we are going to use negative feedback always. What negative feedback is going to do? Why we need to give the negative feedback for an amplifier? We can see here these are the negative feedback amplifier advantages. If we give the negative feedback to the amplifier, it stabilizes the gain of the amplifier. It makes the amplifier stabilize. And it reduces the nonlinear distortions. It reduces the nonlinear distortions or the noise coming to the amplifier. And the negative feedback circuit increases circuit stability. And also it increases input impedance or resistance. While discussing the input resistance, I told input impedance of any amplifier should be high. By giving the negative feedback, we can increase the input impedance. Similarly, output impedance of the amplifier should be low. by giving the negative feedback, we can decrease the output impedance. Similarly, it reduces the noise level. As I said, the second point reduces the nonlinear distortion. It also reduces the noise level coming to the amplifier, and it improves the frequency response as well as bandwidth. If the bandwidth of the amplifier or the frequency response increases, what happens? The different kind of frequencies also the amplifier can amplify. If the bandwidth of the amplifier is less, only particular frequencies the amplifier is going to able to amplify. That's why bandwidth should be always larger and noise factor should be always less. Input impedance should be high, output impedance should be low, and it should be able to address the nonlinear distortion, and it should stabilize the circuit and gain. So these are the advantages of the negative feedback. It will be helpful for an amplifier. That's why we use negative feedback in amplifier circuits. Where we use positive feedback then? We are going to use positive feedback in oscillator circuits. While designing oscillators, we come to know the positive feedback arrangement in oscillator circuits. Now, the derivation of overall gain of the amplifier with negative feedback. We know that gain of the amplifier can be written as A is equal to V0 divided by Vin. Suppose if the feedback is connected, what happens? We will see. So now we can write the overall gain with the letter G. We can represent that with G, that will be equal to V0 divided by Vs. And the amplifier gain without feedback is A, that is equal to V0 divided by Vi. You can observe here, this is Vi and this is Vs. This Vi is the input coming to the amplifier. For this particular amplifier, input and output is considered as V0 and Vi. That's why gain A is V0 by Vi. Overall gain, if we take the circuit gain, that is V0 divided by Vs. So by this expression, we can write it as V0 is equal to A into Vi. Now, what is Vi here? Since it is a negative feedback, we know that the feedback circuit is inverting the signal coming from the output side. Inverting in the sense the phase shift of this signal with respect to the input is 180-degree phase shift. That's why, since it is a negative feedback, we need to subtract the voltage coming from this feedback network here. That's why Vi will be equal to Vs minus Vf. What is Vf here? Vf is the output of the feedback circuit, and V0 is the input here. This is V0, and beta is the feedback factor. That's why Vi can be written as Vs minus beta times V0, where beta is Vf divided by V0 and it is feedback factor. And we can write the expression for Vs by using these two. Now Vs is equal to Vi plus Vf, that is beta times V0. Now we can use this Vs expression as well as V0 expression. We can put it here in the equation 1. If we substitute equation 2 and equation 3 in equation 1, it becomes G is equal to A into Vi divided by Vi plus A beta into Vi. In this expression, we can take Vi here, and in the denominator we can take Vi as common. So if you take Vi as common in between these two, Vi get cancelled, and the overall gain expression becomes A divided by 1 plus A into beta. Now this is the overall gain of the circuit, including the negative feedback. Without negative feedback, what is the gain? A is the gain. With negative feedback, what is the gain? A divided by 1 plus AB. Now what we are going to understand here, this is the overall gain of the circuit, where by including the negative feedback, what happens? It becomes VA divided by 1 plus AB. Now if you observe, the denominator term is more than the numerator. So compared to A, now the overall gain is reducing its value once we connect the negative feedback. Therefore, negative feedback reduces the gain. Gain of the amplifier is reduced by using the negative feedback. But because of the advantages what we have discussed in the previous topic, we need to go for negative feedback for the stability of gain, for noise reduction, as well as bandwidth, widen bandwidth, and the reduction in the nonlinear effects. We need to go for negative feedback. But negative feedback reduces the gain of the amplifier. We need to compromise with the gain, and we need to get the advantage of bandwidth, noise, and all. That's why we need to use the negative feedback. So overall gain of the amplifier with negative feedback is G is equal to A divided by 1 plus AB. Thank you.